Hello, everybody. Thank you for joining our first Simulation Mechanical Tech Support Hangout. My name is James Kubley. I'm a product support specialist here at Autodesk for Simulation Mechanical. Today we'll be talking about weld analysis. So first off, what is a Hangout? It's a time for support team to reflect on what we hear from you, the customers, we support, and to open the floor to Q&A where you're welcome to ask just about anything. And some of you may notice the picture here that is of a Liberty class ship built in World War II. The critical failure there was actually caused by weld failure, though the belief was actually due to poor weld quality from inexperienced welders due to the rush to build such ships for World War II. Only about 12 ships experienced this catastrophic failure like this. So anyways, we're going to talk about different weld analysis. I have a few demos to go through. So the three methods that I'll be covering are welding or modeling the welds as a solid, using the welded contact parameter, and in some situations you may need to generate contact elements to close gaps. So we'll be looking at that method for simulating welds. All of them have their advantages and disadvantages, and they come with assumptions that we will discuss along the way. So I'm going to present these more in a problem statement sort of thing, like doing basic homework in college. So our first problem statement here is we are working with a 1/2 inch thick by 2 inch rectangular steel strap, which is welded to a C-channel with a 3/8 fillet. The welds are 2 inches long, and we're using E70 electrode. The premise of our problem here is that the max allowable stress for the E70 is 70 KSI, and so we're going to use the maximum force that the weld can sustain at failure, up to failure, and see if we actually get failure in our model. I built these models in Inventor. There we go. Sorry, give me a moment here. Looking for the model. There we go. Unfortunately, I had to hand build the actual fillets for the model due to unintended design features in simulation. Unfortunately, weldments do not transfer across from Inventor into Simulation Mechanical at this time. Certain welds do, most do not, unfortunately. So the welds had to be physically modeled in the CAD beforehand. So we're just going to go through some basic steps. We're going to generate the mesh, assign material properties, boundary conditions, those sort of things. And run through a simple analysis. We are using a linear static. We're assuming that deformation is small. Makes for much quicker analysis. So right now I'm just adding our basic constraint. Got to make sure we are statically stable. We do have the welds here physically modeled, but there is a concern right now with this, and that all contact is set to default, which is bonded. So as the model is defined with the contact, the parts are physically behaving as if one part, so the welds wouldn't actually have any effect. So one of the things we want to do is define contact between parts 1 and 2 here. We'll change that to just surface contact. Part 1 and 2 are our channel and our strap here. We'll assign material. Steel, we were using 1080 as rolled. And then for the weld, we'll use a steel again, but my personal preference is just to use a different type of steel. All we're really concerned about is the modulus elasticity and Poisson's ratio, but by picking a different steel, it just helps me visually recognize that as a weld. And then lastly, we're going to add our constraint, or not our constraint, sorry, our load. We're going to go to surface bearing load. Go Y direction. And let's see, our load is, go back to the problem statement again. We're applying 22.28 1,000-pound force. Need to apply that in the negative direction. Okay. All right, we'll run the analysis, and in theory, we should get about 70 KSI, or the material failure, in the welds. Back one. So the advantage of using a solid model like this for the welds is that you can actually see the stress in the weld and perform the analysis on the weld itself. Other methods are going to sort of bypass the weld but hopefully give us the same effect of the weld. Downside, though, of a solid model like this is that it is very mesh consuming, especially when you get to much more larger, complicated models. So right now, we'll just isolate the welds and take a look. And lo and behold, we did it. Our max stress is 70 KSI. We nailed the predicted failure exactly. So let's move on. If you guys have any questions, you can ask them anytime. Sorry, I forgot to mention this before. Ask them anytime. We have a few techs on standby who can answer the questions, and then, of course, we can answer them at the Q&A at the end. So we're going to move on to our next problem. We have two 1-inch thick steel plates that are welded together with 3/8-inch fillet weld. This is, in this example, we are going to utilize the welded contact. And we're going to demonstrate the difference between the two. Between a welded contact and using the just the welds themselves. Again, just going through the basic setup. Got to have a boundary condition and an applied load. There we go. So everybody can see the model. We've got our two plates and our 3/8-inch welds across. Our mesh is extremely coarse here, but that shouldn't be a problem and should help basically just speed up our analysis. I don't believe there was a material type stated other than steel, so we'll go back again. I'll use the same steel I did in the other analysis. And then for our 4 welds around, again, I'll use just the ASTM A36. All I'm really interested in is the modulus elasticity and Poisson's ratio. We're not taking it past yields, so we don't need anything specific past that. Again, boundary conditions, add a constraint here. And then I want to add my load. Add a surface force. We're going the Y direction, and we're going to do 50,000 pounds. I'm going to clone this right now. Go back to this one here. We're doing 2 analyses here. One's to show the difference between modeling the actual welds and using welded contact. Solve the simulation. We are going to then switch to scenario 2 while that's running. New feature in 2015. So in here, we're going to demonstrate welded contact. Again, I have my contact list here of they're all set for default, which reminds me, I apologize, I forgot to set a step in our weld analysis. By leaving it default, the fillet welds have really have no effect because the 2 parts are behaving as if one. So I'm going to set this to welded. Let's see, we have our loads. Let me do a remesh. All right, we'll send this analysis, and I apologize, we'll go back to the first scenario and correct that step. We will set this to surface contact. Basically, the load is going to pull the plate up, and we're going to want the plate to be able to separate from the bottom plate in the center, but we know the welds are going to hold it in place. What it would have done before is it would have lifted up both plates together. And it looks like scenario 2 has finished. And we get a max displacement of 0.014 inches. We can see here that the plate lifted up from the top plate lifted from the bottom plate, which was what I wanted to do. And this was using just the welded contact. So the basis of the welded contact is that all the nodes along the edge here are bonded to the other part. So downside, the reason I couldn't use this with the previous model was that our weld was not all the way around the strap. We only had it on 2 sides. So there is a limitation in its use in that it assumes that all edges in contact from one part to another part are bonded, are welded together. So let's go to scenario 1. My original one, and again we see it lifted up from the center. It did not pull the inside setter all the way up with it. We had some lift, but that's because of the edge. And we can see our displacement there, 0.013. we are just slightly bit off. Our using the welded contact yielded 0.014, and modeling with the welds themselves gave us 0.013. So by using this welded contact, we're able to reduce our mesh requirements, especially as models get significantly larger. As fillets relatively become smaller and smaller compared to the global size. So being able to use this welded contact can help free up needed mesh density for more relevant areas. But the downside of it, though, is it does not allow you to directly view the stress in the welds. You'll have to do a little bit of hand calculations on the side to find out what reaction forces you have going through there and permissible stresses for your welds. This was welded contact. Okay, so there's one other analysis that I want to show you, and that is a limitation with the welded contact in the direction that which the load is applied. We're going to put the load into compression. All we're going to do is simply change the direction of the force and run the analysis. Should only take a moment. There we go. And as you can see, our top plate passed through the bottom plate. Unfortunately, the limitation with the welded contact as such is that only the exterior edges, the exterior nodes, or the nodes on an edge, I should say, are bonded to the other part. The nodes on the intermediate face between these two plates are not matched. They do not have any contact whatsoever. They are treated as free to one another and will pass through each other like this. So in situations like this, welded contact is not appropriate, as you will not get the results you're looking for. But it's still very handy in large models, especially when your loads are, for the most part, tensile and you have very complicated models. And last thing I want to show you is how to use gap elements, or not gap elements, I'm sorry, contact elements. This model is a bit more complicated. I'm not bringing it in from CAD. And I will not be running the analysis as it is a bit more time-consuming. But I will go over the workflow, the steps on how to use contact elements to basically add a weld in simulation. We've got ourselves a basic steel tubular structure here, fixed on the bottom, a force lifting up at the end here. And if we zoom in here, let's see, which one am I? Okay, this is from when I was verifying the model. So if we zoom in here, we'll see that we've got a gap here between the parts. Now we should have a weld all the way around, but it was not modeled, and we need to add a weld. So what we're going to do is use contact elements. We're going to create line elements to join one part to another part. Let me assign this to a unused part number. Okay, so constraint length. This is very handy here. We basically, as defined right now, we're going to have a mess of lines connecting all the nodes on this one face to all the nodes on this other face. This is not what we want. We simply want connection around here where our weld would be located at. So what we need to do is take a look at the approximate length here between our nodes. We're looking at somewhere around 17 millimeters. So we'll set a minimum length of 5 and we'll set a maximum around 20. This may take a couple of tries to get right, and we'll see what we got here. All right, so as you can see, we've got a nice array of line elements that connect our parts together. Line elements are really easy as far as computational requirements. There's a variety of things we can do for this with line elements. We could use rigid elements, which would basically connect the two nodes together and prevent any sort of displacement between them. A very, very rigid connection. It's actually not perfectly rigid. It's just a very stiff spring. What I will use instead is beam. Trusses, unfortunately, well, trusses can work too. They're two-force members. Personal preference is to use beams. You want to define a cross-section to it. I use approximately 2 millimeters. They have, with beam elements, you have a little bit more to play with. You have both the material properties and you have the beam cross-sectional area, which all contribute to the stiffness of the line element. Mostly we're just concerned about transferring the reaction forces from one edge to the other edge. So, and then we'll go with a steel. Here our model is made out of steel anyways, so I'll go through that again here with the other side. In the Draw tab, Contact Elements. We'll set our selection to surface. Doesn't matter the order in which we go. It kept our constraint lengths. We should have very similar constraint lengths here again. And then we'll hit apply, and there we go. There are our line elements, and so we can use this method to help create, when we got real CAD models that do not necessarily have the welds drawn in them or placed in them, and then when you've got gaps to close, when the assumption is that the weld will close the gap, but without the welds actually modeled in simulation, we don't, because of the gap, we have no transference of load in those situations. So contact elements is the simplest and quickest way to generate the connection, the transfer force that we need to simulate and get the effects of those welds. Again, it's similar to the welded contact in that we are not solving for the stress in the weld. We are wanting to simulate the effects or maintain the effects of the weld to solve for the model, but without physically modeling it, to help save mesh density for areas of interest, to keep the analysis time down. And by having assigned that to keeping that to part 5, it used all my element definitions here. Sorry, I forgot to go through the problem statement here for you. So that there concludes the little demo I have on using welds in simulation mechanical. believe that brings us to question time.
Hey James, thanks for all that. There was some questions about, incorporating the thermal aspects of generating the welds and how that, results in distortion, stresses, coming around to residual stress.
So we're talking about the heat affected area from the weld.
Correct.
So there's a variety of things you can do. You could perform a thermal analysis to get the thermal stress, or apply. Let's see. Don't necessarily need to use a thermal stress. Yeah, you can. So there's a variety of ways you can probably tackle it. Off the top of my head, I think the one way I can think of is you can model it in like linear static, or actually more appropriately nonlinear MES analysis. Use a von Mises material property, define the plastic curve for it, run an MES analysis, and then you can, which will then create the deform shape in the results environment. You can then export that deform shape into a new analysis and start from there. The assumption would be that everything's at is at stress-free at that point, but you could get the deformed shape.
So James is correct in, this is Pat Tessero, I'm one of James' colleagues, and I've done an analysis similar to this where a customer was interested in simulating the welding process, and what we did was a heat transfer analysis, a transient heat transfer analysis, where we simulated the intense heat following a trail around an object, and then performing a mechanical event simulation, MES analysis, using a nonlinear material, a temperature-dependent material. We were able to see the tremendous expansion and then contraction, and then learn the residual stresses in those particular areas as a result of it. And of course, all these are always approximations, and they may not represent completely what happens, but it still ends up being very useful.
Thank you, Pat.
So James, one of the more recent questions that came in was regarding the use of beam elements for the last example presented. How do you determine a 2 millimeter diameter? Why not simply use rigid elements?
It's honestly a personal preference of mine. Rigid elements will function just fine, and you can define, it's easier to adjust by defining just the stiffness alone. I use the beam elements because I use them a lot for what am I looking for? Joint and remote loads. So it's just a preference. Rigid elements work just fine. And just to expand on it, they're beam elements, rigid elements, they're all springs. They behave like springs, and because they're connecting to brick elements, they can pivot at their connection point because they can only translate translational loads. They do not translate rotational loads.
Okay, James, here's another question that came in. Your first example used an allowable load of 5.57 K over inch, which includes a safety factor, yet you allowed the stress to go to 70 KSI. Please comment.
There's actually no safety factor with that. According to my reference, that should be the load at failure, 5.57 kips per linear inch for a 3/8 inch weld. But that should be the tensile strength or the ultimate strength at the point of failure. Am I not understanding the question correctly, or?
In the first example, what is the 70 KSI? Is that the shear stress or tensile?
That should be purely shear stress for the most part. If we take a look at it, the von Mises is a magnitude. It's a culmination of all the stresses, but it just happened to work out, surprisingly. Should be this example here.
So I encourage anyone that has questions about weld analyses or any question about simulation mechanical, you're completely welcome to ask anything. In terms of people that are on the question or could also chime in on the verbal discussion. There's Pat, there's Mike, there's Andrew, James, Dean Rose. There's a large team here that can respond. So bring in the questions. We'll be here for another about 25 minutes if people really want to get involved in asking questions. And I encourage a discussion. If things start drying up with the questions, we'll definitely end the meeting early. But please bring whatever you have. If you want to add in a comment in terms of future ideas, you're welcome to do that. But there will be a survey that will pop up when the webinar has ended that will ask you for future questions and how you thought the webinar went and so forth. So I do see a whole bunch of questions now coming in, which I guess hopefully I spurred all that on. So give us a second to kind of digest that and either ask James or someone else from the team to respond, or we'll type them in. But I think at this point we'll probably just respond verbally. So if Pat or Mike or anybody else, as you're reading these, I'm not sure, James, if you're looking at them or not, you're welcome to respond to them out loud.
I see the questions in the chat, but I see answers to them.
So James, you'll want to look at the questions panel. Here's a question for you, James. Unrelated question, how can you create a new coordinate frame if one that loads from the CAD is not oriented correctly?
Local coordinate system. Contemplating just going through that right now for the welds. Let's do that. We'll do a rectangular coordinate system that gives us, that will follow the throat of the weld. Over here, can people still see all of it? I've pulled out the control panel.
I still see a little bit of ghosting.
Okay, let me just hide that for now.
There you go, perfect.
So we're going to go over here. We're going to go to create a new coordinate system. We have a variety of different ways: cylindrical, rectangular, spherical. These just defined, or these just basically tell us how we're going to define it. They all end up applying a rectangular coordinate system in the end to the part. So right now we've got 3 points we need to select: A, B, which A and B define the z-axis for us, and then C. A, B, and C create a plane that then defines X, and then using the right-hand rule of thumb, it then defines the Y-axis. So we're going to set A as this point right here. I like to use edges because we can't guarantee that even if this looks like a square, this is actually a perfect square. So we're going to go this corner here and then see anywhere on this plane. Remember, we're defining a plane, and this is going to be my ZX plane right here. We go, okay. So that creates a little coordinate system for this fillet. We then just need to, well, we can apply, where is it? There we go, coordinate system right here. So it's created. I didn't add a name to it when I defined it, but I can go back and name it. Call this fillet left and go OK. So it should be all I need. So here it is. I can now activate it, and everything will be following that fillet or that local coordinate system. So I'm looking at the YY, which should be the normal stress to the part here. Let's see. Let me show this. That might be easier. Coordinate system, fillet. And so now you can see graphically the local coordinate system are applied here. They are color-coded, blue for Z, red for X, yellow, green for Y. So with that understanding, Y being normal to this face here, we go back here, switch our stress tensors to YY, and we should see stress normal to this face in that direction. If we look for ZX, that should be, there we go. That one, no. I want, sorry, gotta go back, take a look here. I want one, the plane that's in direction with the throat. And that should be the YX. Okay. Here we go. That should be parallel to the throat. Any questions? Would you like me to repeat that again, how to go through the defining a local coordinate system?
There's kind of some other discussions there around the local coordinate system. Let me just read off some of them. Can you make the local coordinate show as one symbol instead of all the vertices? And can you apply a load using a coordinate system that you create? And I think Mike Fiedler just responded to that.
Okay. Yeah, you can apply a load to the coordinate system that you create. You use that for symmetry, especially when your slice plane is not along a global coordinate system. You cannot, unfortunately, reduce it to just a handful of features on the face. It's applied, visibility is to every node. We can make them larger and smaller if we go into the application or the document settings.
If you set the contact to welded, you can also look at the forces in the code. Oh, can you also look at the forces in the codes that define to the contact line to determine the forces in the weld and therefore the stress is correct? In doing this, though, you would have to make sure you use the correct allowables. Forces in the nodes.
I don't know if I fully...
Yeah, I'm not sure if you follow that. Pat or Mike,
fully
did you follow
that question, but if they're wanting the part-to-part reaction forces, this is linear static. Set up parameters. No. Pat, sir, can I get your interjection here? I am looking for train on the part-to-part reaction forces for linear static.
Okay.
And my memory is failing me on that.
if we wanted to assess the reaction forces between parts, then we could take advantage of the reaction force calculator. So by default, the reactions between elements ends up being 0 because each element has an equal and opposite reaction force to each other, such that when we're looking at the reaction forces, we see them at our applied loads and also at our boundary conditions. But, for example, if we wanted to see the reaction forces between two parts that are touching each other, then what we would do is access the analysis parameters, as James is doing right now, and I'll speak slowly. Then we can go to the Solution tab, and then in the lower left-hand corner is the Settings button. And we could disable or ignore the reaction force calculation for a common part. So if I had a part that was sandwiched between other parts, I could disable the calculation for that individual part that is in between several, and then I will learn the reaction forces between the parts that it would touch. So we would rerun the analysis, as James is doing right now, and then whenever we look at the reaction forces, the display is going to be different. So we do this specifically so that we can learn the reaction between parts as opposed to the default configuration where we're going to learn it between the boundary conditions. So if we disable the display of one of those parts, for example, the one with the boundary conditions, then we could see these a lot more easily. And if we were to select all of the nodes that would interact with the other part, and maybe doing so with the displaced model off, then we would be able to see it's just going to get those peripheries. But that might even be fine.
It's welded contact, so.
Yeah. So then we could sum those and see what that total reaction is. Now this is a magnitude, which is going to be different than our applied force because of the Poisson's effect. But if we were to look at change the result type to look at the reactions in the vertical direction, the y direction, then it should match whatever our applied load is.
Mm-hmm.
So one of the questions we had was related to force per distance. So I could select one of those edges and the nodes on those edges and then get my sum. So the nodal selection that we're doing right now is fine. And if we just do a rectangular selection of one of the, like the right edge of this view, then we could see what the force is over that distance. And we could see the total force, or we could right-click on the screen, and this might be even more helpful. We could choose to create a path plot, which is near the bottom there. And then, oh, wow, and then sometimes we get a software crash like this, which makes us all feel a little silly, doesn't it?
Yay.
But James will recover the model, and when he does, we'll be able to take a look at the path plot. And when that comes up, it will be showing our result based off of the distance between the selected nodes. So I think that that's going to give the kind of result that was requested specifically in the question we had earlier today. So we'll be patient as James feverishly brings up our results environment.
Isolate. We want
the y direction in this case.
Force y. Ah, there we go.
Now we want to plot this. So it's either going to be the x or the y direction. So why don't we right-click amongst the nodes, and we could choose to sort. This will be in the path plot definition window. So that window inside will have the white area that has the node numbers.
Got
You
it.
can
Okay.
sort by X. There we go. So now we see what the reaction force per distance is for this particular weld. And we get we could have had the inquired sum result, which would be the average reaction force per distance. And this gives us a more accurate representation of what that force per distance is, and we can see that there's a peak value which becomes very important to us.
Well, Pat, while you're talking, there was a question that came in. Here's how they phrased it. Pat discussed an example for thermal welding analysis. Is there an online example or other resources that discusses this in more detail? So basically anything in a help or knowledge-based system about this?
That is a good question, and I don't know if there's something immediately accessible. So I think probably putting something together might be a good example. So we've had a couple suggestions today on future topics, and because this is the first installment of this type of presentation, we had to start somewhere, and the fact that we're having this discussion is good. So maybe the welded analysis simulation can be something we could take a look at a future presentation, as well as the recommendation for I think there was a composite or that was one of the first comments here. Any chance you guys could do something more complex like laminates over materials with anisotropy material properties? And John, that's a good recommendation as well.
So while you guys were talking, there were some more questions that came in. Is there a recommended practice for determining stitch weld pattern or sizing? Is there anything there?
Are they referring to the
Go ahead.
contact elements, the contact elements I created, I'm assuming?
Well, that's all that Kevin wrote in, so if you wanted to add more information, Kevin, you can add another question.
Well, I'm familiar with stitch welding, and unfortunately or fortunately, I have a history in mechanical repair and welding, so which makes doing finite element analysis so much more enjoyable. So with a stitch welding, I'm welding, and then I have a space between the next start of a weld, and it's a way of saving material and effort, so I don't have to have a continuous weld around the periphery. And we can create our model. In this case, James had examples where the weld was continuous, but these welds could be shortened and more numerous, and that would be one way of considering a stitch weld, and that of course would allow you to assess the force per inch or stress or any other result that you think is an important criteria for determining the weld acceptability. There's other techniques that would allow you to not have the weld in there at all, and maybe that's something that we could look in, and of course for a future presentation, but of course whenever you do these approximations, then you're obtaining less detailed results as well. And so the idea is when you're approximating the details of something, you're looking at the overall results and more like the stiffness and deflections of the model, or maybe the stresses in other locations, not necessarily the stresses in those particular locations.
Okay.
Pierre congratulates us, so that's very pleasing.
Thanks, Pierre. So we have a few more questions. We have about 5 more minutes, so let's see what we can do here. When I performed...
Actually,
Yep.
Oh, I'm sorry. Go right ahead.
Yeah, so there's another one from Pierre. And maybe this goes along with what you just talked about. When I performed weld analyses, I would like to run a simulation to connect the nodes at the location of the weld, and then select these nodes in the area of the highest value divided by the approximate length to obtain the force per inch. Then I refer the AWS welding code to see if this was acceptable. Does this sound like a good approach?
Well, you know what? It's a subjective question. The responsible thing that I could say is, we could discuss the ramifications of whatever technique that you want to use. And ultimately, although I'm a professional engineer, it would be not quite appropriate for me to say, you should do this, or you should not do that. So I'm going to be limited in to that extent. But I'm trying to look for where that exact question was listed here. Is that at the very bottom?
It came in around 1040. If that helps you.
Okay. Yeah, it does. So that's going to be 1140 on my computer.
That's right.
Okay, when I perform a weld analysis, I would run a simulation to connect the nodes at the location of the weld, and select these nodes in the area of highest values, obtain the force per inch, and then refer the AWS welding code to see if this was acceptable. Actually, you know what? That does make quite a lot of sense, and our example, which is still vaguely displayed in the background of making a path plot, not only allows you to identify what the local force per inch is, or load per distance, but see what that magnitude is, and the chain is as strong as its weakest link, so that would make appropriate sense. And of course, there's limitations of a linear analysis, and as far as local yielding not being considered, and that load therefore being taken up by adjacent material.
Okay, so Boris had a question here about singularities. Is there
Yeah,
a way
that
to
was a good question.
Yeah, is there a way to distinguish between real stress and singularity response?
There is, and if I am under the belief that I perform a finite element analysis and I press all the buttons one time each, like mesh and analyze, and I see results and think that those results are complete and satisfactory, then I'm making a mistake. I'm only getting a small part of the picture. And the way that we can identify a singularity is by doing a mesh convergence study. This is where I identify areas of significant results in my model, and then incrementally I decrease the mesh size in those regions and then reanalyze. And then I could reassess those results in those areas. So what I want to do is I want to converge on a result. And stress is usually the most temperamental thing to converge on. And if I have a singularity, what will not happen is I will not converge on a stress in a particular area. And so that mesh convergence study is a way that I can identify singularities and therefore determine the quality of my my results. But as far as reaction forces, they're going to be quite similar between parts. So if my goal is to get the reaction forces, I may not necessarily have to do that convergence study. But if I'm looking for stresses, then I do. Royce says that we have just seconds to go, so I'm going to stop talking and let him continue.
Thanks, Pat. That was a good thing, I think, to end on. I just want to thank everybody for joining today. Just remember, we're going to have a survey that pops up as soon as you leave the meeting. Please fill that out with as much detail as possible so that we get the ideas that you want to hear. Remember, this is the first one on mechanical, and we've been doing this for a while with the CFD package, and we're really trying to drive those future meetings on those responses. Also, there will be a YouTube video posted hopefully next couple of days, and there will be an email that comes around from Kate Perez with the link since you joined and signed up and everything like that. These meetings for each product, it's kind of be a rolling schedule. So next week we're going to be talking about our composite software, then back to CFD, then MoFlow, the mechanical, and then composite again, and keep rolling from there. So you'll get many more of these meetings in the future. So don't feel like if you were left out today, you'll definitely get your opportunity on mechanical at least in the next month. So again, I thank everybody for joining, and you have a great rest of your day.